Hello and welcome. Today we're going to do an introduction of linear systems of equations. All right, so a linear system of equations is fairly simple. So let's talk about the word linear. A linear equation. So many of us from algebra have a pretty good understanding of this. We can write down a linear equation. One such equation would be y equals mx plus b. All right, let's see if we can write this one. We can draw this. So obviously here, m is the slope, and then b is what we call the y-intercept. Okay, and we're all familiar with drawing graphs of these sort of functions where we have that value there on the y-axis is b, and here that m is the slope. Okay, and that is y equals mx plus b. Okay, all right, so that's all well and good. All right, and there's another form. Of linear equations. We can write this down. Another form of y equals mx plus b is actually write it down as ax plus by is equal to c. Where now the b that I've put there is now going to be a different b than it is here. We can see we can always revert this back. We can always write our equation as y is equal to minus a over b x plus c over b, right? Where that right there is equal to my m, and this is equal to my my y-intercept. Okay, so but this form is a little bit easier to manage on a day-to-day level, so we're going to really go with this form. Okay, so this is a linear equation, and I'll give an example of a linear equation. We could have something like, well, we just have a very simple one. X plus y is equal to 1. All right, and we can give, and we already know what this equation looks like. I can put it into slope-intercept form as simply 1 minus x, and we can draw that on here as follows. And at the value 1, we put a line that goes like that through it as follows. And there at x, so this is the x domain, and that's the y domain. And let's see if I can get a better, oops. That's the best I can do as far as a graph there. All right, so this equation, so this is a single linear equation. And then, of course, it has two variables. Okay, so the question, or what do we want to talk about when it comes to these linear equations? This linear equation, the main question we want to ask is, what combinations of x and y satisfy the, I'll call it right here, we'll call it LE, just to keep it simple, the LE. Okay, and it's pretty clear here that the answer, at least in this particular case, is going to be, there are many answers. There are many combos. Okay, so we can think of some examples here. Obviously, the combo, so I'm going to put this as actually an ordered pair. Combinations is an ordered pair of x and y. So if I put, here's x and that's y there. So if I put x, if I put 0 there, then y has to be 1. That is one such value. And of course we see that that's that value right there. Right, and there's another value, of course, at 1, 0. And that's that value right there. You can think of others. I could, of course, go 2 and minus 1, right? And that's going to, of course, be right here. And, of course, we could do 100, of course. And, of course, then we would have to have y be minus 99. Okay, and of course that's would be somewhere way, way, way down there. Okay, and the list goes on. So what we actually see here is that there's infinitely many solutions. So that's a solution, but all these points in between are also solutions, and that's what forms this line, okay? So there are infinitely many. There are infinitely many solutions. And we'll find out later, of course, that this is sometimes true that there's infinitely many. Sometimes there are no solutions. Sometimes there'll be just one solution. So we got to expand what we mean. Right now we're talking about a single linear equation. What about if I have multiple linear equations? So now we're going to talk about systems of linear equations. What I mean by systems is we're going to have multiple LEs. Okay, so we're going to have multiple LEs. All right, so let's do an example here. I'll start with that before. We have x plus y is equal to 1. That was a linear equation we had before. And then we're going to try another one here. We're going to do negative 2x plus y is equal to, we'll say 2. Okay. All right, so now we're going to ask the same question. The question then again is, what values of x and y, what combination of values of x and y satisfy this, what we call now, what we're going to call here is the actual, what we call a linear system, or what we call LS. Okay, all right, so we can, first let's explore this graphically. I'll draw that graph again, and at 1 and 1, we have that line that goes through like that. And that's that first equation. That's what I'll call LE1. And that is going to be y is equal to 1 minus x. And then we have another equation here that it's going to be up here. I should have drawn this better. I'm going to actually change my equation just slightly and make that a, let's say, we'll say it's 0, okay? And then what we're going to do is it's going to pass through that point there, and we're going to go up. And when we go 1 over, it goes up 2, so it's going to kind of go like that, like there. So there is an intersection point. So before, with the first linear system, all these infinitely many solutions that were on this line, and that was for the first linear equation. But now we're asking this additional question then is that the x comma y combinations have to satisfy both equations. So x and y must satisfy both LEs. Okay, we see that there's one crossing point, and that is the single solution. So let's see if we can find it. Should be easy enough to find. Of course, we have y equals 1 minus x. We also have y equals equals positive 2x. Okay, so the y's have to equal, and that means these two have to equal as well. So we can have 1 minus x is equal to 2x, and that becomes 1 is equal to 3x, and that means that x is going to be equal to 1/3. All right, so we have the first value there, and of course we can plug that value into there, and we get that y is equal to 2/3. So our answer then, the answer to our question is going to be a 1/3, 2/3. That's my x and my y. All right. All right, so now we see another outcome. So the outcome so far, the outcomes were 1, infinitely many solutions. Now we saw a single Okay, and it begs the question then, what about none? And it turns out that is also a viable answer for a particular linear system. So let's now see if we can find that third outcome by switching to yet another linear system. Okay, so this time, so we're going to talk about now a new linear system, LS. Our LS is going to be as follows. It's going to be, again, I'm going to start with that equation we've done so many times. X plus y equals 1. All right, and now what I'm going to do is I'm going to say we have now a negative 2x minus 2y is equal to negative 2. Maybe not. We'll try 1 there. Okay. So let's look at this equation now and see if we can come up with what it looks like. So again, what we're going to do is we have this. That's the y equals 1 minus x line for that first linear equation. Oops, sorry guys. Okay, and then now we have to find this other equation. So I'm going to do a little bit of moving around here. So I'm actually going to divide by negative 2, and then we're going to get y is equal to negative x minus 1/2. Okay, so let's see if we can come up. So that's actually going to be down here. The y-intercept then is going to be at minus 1/2, and it's going to go like this. Okay, so we see, of course, here that lines don't cross. Okay, so what we say here is then we have no solutions. Okay, no solution at all. So again, our outcomes, we can have infinitely many solutions, one solution, and then none. Okay, so these outcomes, it turns out, are true no matter what linear system you're talking about. These are the only 3 outcomes, no others. So, for example, you can't get 2 solutions, or 3, or 4, or 5, or something else. You can either get infinitely many, 1, or none. Okay. All right, so let's now, some more terminology here. The terminology I want to detail is pretty simple. We're just going to talk about now the solution set. I'm going to call it capital S. I'll put the little serifs on there. And so S is basically, we can write it as follows. S is equal to, and this is all in set notation, it's going to be x comma y, it's combinations of x comma y, given, all right, so this right here, when I write this, this tells you what kind of objects that is telling you the type of object. In this case, it just means, in this case, it's an ordered pair. Okay. All right, and then this right here, this symbol right here means given, or subject to the following conditions. So we could say something like that the linear system is satisfied by x comma y. We could also write other things. We'd actually write out the equations in here. Okay, we could do a lot of things to express that, but this is the solution set. And while it might not be so important to be so formal in defining this in a set theoretic way, we'll see later on in later videos how being able to write things in this very crisp, very specific way can really help us understand what we're talking about. The idea that the main object is to study the nature of these solution sets. And so we might as well give it a name and have a way of talking about it using concrete language. All right, so now let's go and discuss a little bit more some other cases. Of course, now, so in general, so far, I should say, so far, what we have is we've had linear systems had two variables. For these two variables, but that's not always true. You can also have n variables, and also we could have m linear equations. So another example would be that of a 3x3 system. And what we mean here is there's three variables. So for instance, x, y, and z. And then there'd be three equations. Okay, so let's write down an example linear system of three equations and three unknowns. Okay, so here's such an example. We can write out x plus 2y plus z is equal to 4. All right, we can also write out 3x, so that's the first linear equation, plus 8y plus 7z is equal to 20. All right, and then finally 2x plus 7y plus 9z is equal to 23. All right, so I'm going to put little brackets around this to kind of organize my system. All right, so this is now so we would say something like 3x3 linear system. That's what we'd say this is, okay? All right, and then what we're really interested in again, the question of the day is always, what is the solution set? So again, S is going to be this, right? It's going to be this set. And now what's in the set? Of course, it's going to be ordered triplets, x, y, and z. And okay, subject to whatever the linear system is. Okay, that it satisfies this linear system up here. And so that's the type of set we're looking at. Okay, so now again, I'm going to write this down more formally then. So we saw before the outcomes. We had three different outcomes. So it turns out that's always true. So we can actually write this down as a theorem. So the theorem is, given a linear system of n variables and m equations, the solution set S has either infinitely many solutions that's one. Of course, one solution, or three, no solutions. Okay, so in this case, of course, S would just be equal to, some single value, call it x1, x or y1 and z1 in this particular case, right? And node solutions asks, how would we write out set theoretically what node solutions is? We'd actually say that S is the empty set, like that, okay? All right, and infinitely many solutions, of course, we'd have to express that in a more complicated way. All right, so now I think we have some basic nomenclature down to talk about solution sets. So the question is for complicated LS systems, linear systems, how do we find how do we find S? And the idea is we actually have to develop a procedure to find S. Okay, and those procedures are going to be called row operations. And in later videos, we're going to talk about those row operations, how to do it. So in the next video, we'll detail exactly how to talk about row operations, and we're going to do it first on that linear system that I wrote down on the previous page. Okay, so again, I'll write that down. It was this linear system right here. We'll actually figure out and learn some procedures to actually find out what x, y, z is. All right, so I hope that this video, of course, was lots of just going over nomenclature, defining a few definitions, and getting a sense for the nature of the problem. And in the next video, we're going to talk about how to actually get to the solutions. All right, thank you very much.